Okay, in the previous class, guys, we had spring and damper, right? And we saw that output over the input of the system as a first order system was tau s plus 1, a stable pole on the left hand side, and we applied f of s as the impulse, which was 1, and we saw that the error signal was 0, right? ESS was 0. Also, we applied the step input as 1 over s, and we saw also that the steady state error signal is 0, right? So here is the answer. So ESS also was 0. Can you hear me, guys? Yes? Can you hear me? Okay. Now, going ahead, I want to introduce another the first order system. Okay, and we saw that the pole of this first order system is here, minus 1 over tau for the real axis and for the imaginary axis. So the other system that I want to introduce here for the ramp input is the RC circuit. Because we had 4 inputs to the system: A, impulse; B, unit step; C, ramp; and D, parabolic. So we did these two for the spring and damper. Now I'm going to go to RC circuit. It's going to be R and C. And this is input voltage, plus minus. So you know that always current goes from the positive to negative, from higher potential to lower potential. That's right, because voltage means potential. That's right. Voltage means potential. In mechanical engineering, potential. That's right. So what I'm going to do, I'm going to measure the voltage of capacitor VC. So I want to drive output voltage of capacitor over input voltage. So this is going to be my closed loop transfer function. I'm going to do that. Okay. How to do that? Kirchhoff voltage law. So we know that the V in equals to voltage across the resistor. So VR plus VC, right? So what we know that from Ohm's law from high school, VR for the resistor is RI, resistance in the current that is circulating in the circuit, plus VC. What we know from elementary physics that in the capacitor, current is C dVc over dt, or we know that the VF capacitor is 1 over C capacitance integration of I dt. But I just want to work on this. Okay. So I'm going to implement this here. Okay. If I do that, you're going to get RC dVc over dt plus VC. Now these are time domains because you have time derivative. So if I want to go to frequency domain, what I have to do? You tell me. What I have to do if you want to go to frequency domain? Anyone? Yes, Laplace transform. Assuming that the voltage at time 0 Vc is 0, okay, and V dot first derivative voltage is 0, okay, so you get from here that simply RC VCS time domain plus VCS equals to V in S, and you have an S here because this is the first time derivative. That's right, remember from the Laplace transform. So if you factor out from here, you get VCS RCS plus 1 equals to V in S. So, as I promised, RC is VC, I'm dropping S over Vn equals to 1 over RCS plus 1, showing that the RC circuit is a first order system because of this. Bingo. Now you tell me, what's the name of this I told you? What's the name of this RC? What's the name of that? Huh? What's the name of RC? What's its name? What's the name of that? Yes, time constant of the circuit. Here we go, time constant of the circuit. So this is the RC closed loop transfer function like as the spring and damper. And they have the same closed loop transfer function. The difference is that for the RC circuit, time constant is RC. For the spring and damper, time constant was C over K. Here we go. Clear? Yes? So now you see that by having the same transfer function, whatever I applied by applying the impulse and the ramp is valid for the RC circuit. I don't need to do that again. So RC circuit subject to the impulse input, error signal is 0, means the capacitor voltage gonna follow the input voltage. By applying the step input, step voltage. When I say step voltage, what do I mean? In electrical engineering means V in like is 20 volt. So this is step input, that's right. See here, 20 volt or DC voltage, that's right. You heard this, DC voltage, AC or DC. So DC voltage is 20 volt, so it is step input. Not unit step, but step input. So see that error signal goes to 0. Now I want to examine this. If I apply the input voltage as ramp, see how it behaves for this first order system. Can I go to next page? Huh? Already? Okay. So until here, I proved that this spring and damper, as I promised you, subject to external force, dynamically they are the same system with RC system as a first order system. RC, KC. Why? Because their transfer function we derive together, their closed loop transfer function was this 1 over tau s plus 1. for solar system. So this is how the skill that you have to learn. You have to find the analogy between the systems. When you see RC circuit, you can visualize as a spring and damper. When you see spring and damper in your car suspension system, you can visualize as RC circuit for designing digital controller. Huh? Interesting, right? You see what I'm saying? Yep. Okay. Now let me, as I promised you, and this is equals to VC for this over Vn. So I'm saying now input voltage, third case, is ramp. Means this Vn T. This is ramp, straight line. Here is 45 degree. Means that you linearly increasing the voltage, input voltage in the system. So having that, we know that the Laplace of this, from whatever I taught you, we in S gonna be 1 over S squared. Remember, you have your Laplace transform. I'm gonna implement here. So you're gonna have VC gonna be 1 over S squared 1 over tau S plus 1. Because I want to see when I apply the ramp voltage, what's gonna be voltage of the capacitor. Voltage of the capacitor. And as you know, because this has repeated roots or poles at 0, okay, so it includes 1 over S squared, 1 over S. When I decompose this, I have to decompose like this: A over S squared plus B over S plus C over tau S plus 1. If you forget to do this, you get the wrong answer. It's trivial mathematics. Now you can write this as very trivial solution is S squared tau S plus 1. You're gonna be A tau S plus 1 plus BS tau S plus 1 plus CS squared. And this is equal to 1. So simply, you get this. See, I'm sorting based on this. It's gonna have B tau S squared. Sorry guys. B tau S squared plus C S squared. So plus A tau S plus B S, that's right, plus A is 1. This one. This A is 1. Understand? So obviously having that, just here is no S squared and here is no S, you get B tau plus C is 0, A tau plus B is 0, and the A equals to 1. If you put this here, you get B equals to minus tau, and if you put this B here, you get C equals to tau squared. So we found the coefficient. So voltage of the capacitor based on the ramp input gonna be 1 over s squared minus tau over s plus tau squared tau s plus 1. Clear, guys? Yes? So now I want to find in time domain solution. I have to apply Laplace inverse. Can I go to the next page? Yes. So having that, you get Vc in time based on the ramp input. So we know that which function gives you 1 over s squared? Ramp. So you're gonna be ramp t. Which function gonna give you 1 over s? You tell me. Now you know it. Step. That's right. So you're gonna be minus tau because step is 1. Unit step is 1. And now which function gonna give you this? Because you can write this. Let me teach you guys. You can write this as this tau s plus 1 over tau. So this which function gonna be exponential, that's right. So you're gonna have plus tau e minus t over tau. Here we go. We found it. So let me plot this. Let me plot this to see how it behaves. Voltage of capacitor versus time. When time is 0, guys, Vc at time 0 gonna be 0 minus tau plus tau. It is 0 here. When time goes to infinity, a large number, Vc gonna be how much? This is gonna be 0. That's right. What is this, guys? You tell me. When time goes to infinity, Vc equals t minus tau. Right? Do you confirm it? Yes? Now, can I write like this, guys? Look at here. Look at here. Vc minus t equals to minus tau. Can I write this like that? Yes? Okay. So what is t? What is t? What is t? Input voltage, that's right? Yes? So it's gonna be Vc minus input voltage is tau. What's the name of this in block diagram? Look at here. Output over input. What's the name of that in block diagram? If I want, look at here, guys. V in plus minus goes to 1 over tau s again upon the transfer function Vc. V in minus Vc, or say this is tau, so minus tau. I mean V in minus Vc gonna be tau. V in minus VC. What's the name of the signal? What's the name of that signal? Huh? What's the name of the signal? V in error signal. So it says you have this constant error signal. You have a constant error signal. Despite the cases of the impulse and step for the ramp input, we have a steady state error signal and it's constant tau. Understand? So I'm just deleting this now because now you know everything. Okay. So on the other hand, you see that also I'm deleting this. You see that VC is equal to V in minus tau. So whatever your voltage input is, look at here guys, this is your input voltage. Here is 45 degree. 45 degree. This is V in. So your voltage of the capacitor is tau amount lower than the V in. So it's gonna be like this. Here we go. See, here we go. Let me change the color because I can't favorite that. So it's gonna be like this. Here we go. And how much is this, guys? You tell me. How much is this difference? How much is that? How much is that? How much is that? Yes, guys? Tau. Tau is constant everywhere. Here's whole, here's tau, whatever. So you see that you have steady state error signal, tau. See what I'm saying? Now, having this, let me prove it by final value theorem. Okay, saying ESS is a limit of S V in input to the system 1 plus G when S goes to 0, as I told you. This is a limit of your input is ramp, so it's going to be 1 over S squared 1 plus open loop transfer function 1 over tau S when S goes to 0. This with this goes to New York, so it's going to be 1 S plus 1 over tau. Because when S goes to the denominator, it's going to be like this. When S goes to 0. When you put S0, 1 over tau is tau. Bingo. We found that. And obviously, if you increase tau, if you increase this tau, your error signal is going to increase. Time constant. See what I'm saying? If you increase tau. This way is for you increase tau. If you decrease tau, error signal is gonna decrease. Clear, everybody? No, it's a straight line. It's a straight line. Here is kind of the curve, okay? But after here is it cannot be parabolic, man. It's parabolic means that tau is increasing. That's right. I'm saying tau is constant. Okay? But here must be a straight line that keeps your tau constant. Understand, everyone? So let me go to the Mathana Simulink, and as we did for previous cases before going to parabolic, and we run in MATLAB. Then we go to tank of water and then the input of parabolic. Then we're gonna go to input of the harmonic for Bode plot for the first order systems. Okay, but before going here, let me show you guys. First, I'm gonna go here and okay. And if I save this as first for coding, okay, as ramp first order, okay, guys, I don't care about this then for now. If I say ramp, I just give it just numbers. I just want to show you. It's gonna give you error signal. Look at here. Because MATLAB encoding, like as impulse, has no ramp command. Only we have step, only and only. So what I'm gonna do, I'm gonna reformat as we did for the impulse. I'm gonna reformat the transfer function. Look at here. Vc over Vn is 1 over tau s plus 1. So, but your input to the system is what? Is ramp. This is ramp. Gonna be 1 over tau s plus 1. But you can write this ramp as 1 over s in 1 over s. Yes or no? So what is this now? You tell me. Now you know it. What is this? Which input to the system is 1 over s? Look at your notes. Yes, step. So now because we have step command in MATLAB coding, that's right. So Vc gonna be Vc over step. Now I'm multiplying, moving to other side. It's gonna be 1 over s tau s plus 1. Or you see that it's gonna be tau s squared plus s. I reshaped closed loop transfer function as first order to second order, but with the input of the step. It's gonna give me the ramp response. For example, let me examine tau equals to 2. So here, by having this, you have numerator, you have no zeros. Gonna be, because it's second order, so it's a 0, 0, 1. Second order, you have to go like this. The denominator gonna be tau 2, 1, 0. Everybody understand what I'm talking about? Yes? Everyone understand what I'm talking about? Yes? Clear, everybody? Numerator, denominator here? Yes. Good. So now I'm moving exactly this to the MATLAB code. I'm gonna share with you. So here gonna be your num gonna be 0, 0, and 1. Your d gonna be 2, 1, and 0. Exactly as I told you here. 2, 1, and 0. So if I plot this, now I'm gonna put this step again. This is for ramp, but I reshaped it close to transfer function. I'm gonna just put this here, and here is it is titled is ramp first order. You see that if I run this, it kind of gives you the ramp inputs as exactly I promised. See, this comes and then straight line. See, ramp first order. So if I want to say hold because I want to compare with the input, So you're gonna say y equals to t. This is the ramp, that's right, in high school, remember? So you're gonna say hold plot time and y in red. Oh, see, I'm gonna make it say to 20 seconds, because this is ramp, that's right, y equal to t, as I taught you. So oh, time. Sorry guys, time is this. Okay, okay. Oh my god. Okay. All doesn't comes up. Okay. Hello. This is blood. Oh, I see. Figure one. Let me see if it hopefully. Yeah. I forgot to put figure one, so it's plotted. So this is the ramp input, 20, 20, the red line. And this is what? This is the voltage of the capacitor. And here is time constant. See? Here must be 2, because your time constant is 2. Okay? Let me show you. You have to prove it. Look at here. If I zoom in. If you zoom in here, see? Here we go. Here is 2 seconds exactly. See? 10.2, 8.2. It's 2 seconds. 2 seconds. 2 seconds. Red is input to the system. Let me show you. Yeah, red is input voltage. Input voltage. Red is the input voltage, and this is the voltage of what? What happened? Oh, that is the input voltage, and the blue is the response of what? Under the ramp. With tau is 2. See what I'm saying? So, did you follow the course in the class? So what is this screen? What is this screen? No, this screen. What is this screen? This green line. This green line. Or what is this red line? What is the name of this? Can you read this? So what does it mean? Means voltage of what is VC? Yeah. So we are finding voltage of capacitor for the input. That's right. This orange line. See what I'm saying? So this is the same. So, okay. So this is the ramp, and this is the response. See what I'm saying? The blue line is response. Clear? Yeah, exactly. So this is for the time constant of 2. See what I'm saying? So, and now if I increase, good that you asked that, because maybe it's a question of other students. Okay. Now, if I increase that, as I told you, the time constant to 5, you're gonna see this, the red line. the error signal increasing, that's right, as I showed here, right? So let me plot it and show to you. So, and I'm gonna say, hold on, and now I'm gonna plot this step then 2, and this is gonna be for tau is equal to 5. When I increase time constant to 5, so you see that what the hell is this? Oh, I see. And always, guys, put this in your code. Means clear the workspace and clear all the parameters for that. Okay. Are you kidding me? $510. Okay. Let me put it here. Now, then to time. Why it doesn't plot it? Okay. Yeah, there we go. You see that I increase the time constant to 5, you have more error signal. That's right. So if I zoom this in, this area, there we go. See, here is 2 seconds, here is 5 seconds. See, 5 seconds. I mean the 5, and here is 2. Difference between the voltage. So difference between this voltage is 2, there's 5, because I increase the time constant. Okay, here we go. And obviously, if I decrease the time constant to 1, you're gonna have this here, this line between them. You are decreasing the error signal. Clear? Yes? So, any question, guys? Any? If you are done with this, let us go to the Simulink. Because in Simulink, we're gonna do the same. And don't forget, guys, in the coding, you are putting the closed loop transfer function. Closed loop transfer function. Okay? So in the Simulink, until this comes up, I'm going to examine this open loop transfer function. Because in Simulink, we have a ramp command. You don't need to reshape your transfer function. We're going to stick to this. And open loop transfer function. See? I'm gonna just take this on the new Simulink file. Here we go. And also one of these. Here we go. Okay. We don't need a step. We just put the library browser, ramp. So I'm gonna put the ramp here. See, we have ramp in the Simulink. We don't need to change everything. We don't need delay. Oops. Okay. There we go. So what we're gonna do, first order system. We don't need to do 1 over tau. I'm gonna say tau is 2. That's right. tau is to 2, 0. 1 over tau s, first order system. That's right. See, 1 over tau s, 1 over 2s. Here we go. I'm going to delete all this. Okay. And why I'm putting this, because I'm gonna, let me first double click on the ramp. So slope is 1, means 45 degrees, starting time 0, initial input is 0, obviously. Okay. So I'm gonna copy paste on this as I did in coding. Okay. I'm gonna put 1 over 5s. I'm increasing time constant to see, to visualize what? To visualize the, I'm saying a Simulink ramp. I'm gonna share with you. First order system. There we go. So, okay. Right click, put this here. Right click, put this here. Now I'm gonna double click on mark because I want to see the output. I'm gonna put number of the inputs 3. Apply this. Why? Because I'm gonna take from the input to the output to be compared. And showing the error signal is tau. So I'm saving this as we did in MATLAB. You see that Simulink is much easier. So, and run it. Here we go. As we expect to see. Exactly as we did. See? Constant error signal. Here is 2. Here is 5. Here is 2. Here is 5. Forever. Clear, guys? Yes? Everybody?
Yes.
So, now I'm going to show copy paste. Double click like that. To 2. Now I'm going to take from the error signals to show it that error signal is constant. That's interesting. And one of them goes to 2, one of them goes to 5. See here. To avoid confusion, I'm just putting this like this. And because I'm going to share with you. Okay. So save. We're going to see in the first 2, one of them 5. Let me increase to 20. Here we go. As you see, one of them goes to 2, another goes to 5. Need more time for the output for 5. So let me put 30. 30. Here we go. This is 5. I'm not sure that you can see or not. But 1, 2, 3, 4, 5. No. Oh, it's 1, 2, 3, 4, 5. Here's 0, guys. 1, 2, 3, 4, 5. See? And this is 2. Error signal is constant for this first order system, which is subject to the ramp input. Okay? What I'm sharing with you, I want to make sure that you know this is the error signal. This is error signal. Okay? Understand, everyone? So this means if I put the spring and damper also the ramp, you're gonna see the same response. It doesn't matter. That's why I told you that I'm gonna prove the spring and damper, tank of the water, and the RC circuit, they are the same system dynamically. And you can make an analogy between them. See what I'm saying? Yes? So now can I close this? Everyone? Okay. Now let me close MATLAB. Let's give you hints that what we're gonna have for the next class. Okay. Okay. So now we applied A as this impulse, B as the unit step, C as ramp as input. Now D gonna be parabolic, but where for this system? You have outlet flow rate, Q out, inlet flow rate, Q in, around the equilibrium point, and you have h of the fluid, height, and this, if you passed, guys, how many of you passed fluid mechanics course? How many of you passed the fluid mechanics course? Huh? Okay, good. So you know that here is a resistance for the fluids, right? So that's why we are showing exactly like as resistance, like as a valve, like a valve here, okay? So we are saying that resistance of the tank, resistance of like as the resistance of the electric circuit, okay? And you know, and obviously you know that a tank of water has a capacitor, has a capacity, like as the capacitor of the RC circuit. We are showing it as C tank, CT. Okay. So for the next class, I'm gonna derive this first order system, and I'm gonna prove you that the tank of the water is exactly like as the RC circuit, exactly like as the spring and damper, but subject to this parabolic inputs. Okay, everybody, clear? Huh? So any question you have? Anyone? If you need clarification? Hmm? Okay, so let me, if you don't have any question, let me close this and